SwayamPrabha. Digital India. Educated India.
So as I said, we are trying to progressively incorporate the ingredients into the model. We discussed already a few items. So for example, mechanics, how mechanics plays a role, how microstructural anisotropy plays a role. Now what we're going to do is the electrochemistry, right? So the people will say, oh, you know, electrochemistry is a big deal in corrosion, so you need to account for electrochemistry. And they're right, electrochemistry is important, so we need to account for electrochemistry. Well, you can. I mean, the models start to become a bit big. You're seeing here the equations, but you can solve for those. So you can see here what you end up with is, you know, you have an equation for the corrosion, facial corrosion. So again, it's the same equation that I showed you before. Then you have one for the transport of solid phase ions, or the metal ions. That's the one we discussed before. But now you have an extra one, which is the transport of ionic species. And this is CI, which means that any ionic species that you're interested in, you may have 5, 10, 3 ionic species that describe your electrolyte. You need to solve this kind of Nernst-Planck equation for all of them. And then finally you have the electrostatic potential distribution. So kind of the Gauss law. And I think the only things to highlight here is, first you need to take into consideration that when I show you at the beginning the Nernst-Planck equation, so these are well understood equations, because we are solving them in the entire domain, because we need to we don't want to solve them in the electrolyte, you need to use some sort of interpolation function. I think that's the only thing you need to consider. So these are the couplings that one has to be aware of. But in any case, the idea is that in principle, why not? We know what are the PDEs that describe electrochemistry, so we could add them to our system. And when you do that, you can capture the phenomena that you expect to see. So you can capture, for example, the effect of the solvent concentration. You can see here how the solvent concentration impacts peak depth. You can capture the effect of the applied potential, and you can see how the electrochemistry evolves with the shape of your corrosion front, as you would expect. So again, you know, the model is becoming heavy. We have more and more degrees of freedom to solve, but it is doable. You can incorporate this phenomena if you're interested in. Whether this is a first order effect or second order effect depends, you know, how much, under what conditions and what problem you're looking at, but again, we can incorporate the electrochemistry. The other area that I'm quite interested in is the degradation of magnesium in body fluids. So this is what people call biocorrosion. So here we're moving a little bit around. So instead of talking about you know, engineering alloys in engineering applications, here we're interested in what happens inside of our bodies. And the idea is that, you know, whenever you have, if you fracture your leg, then you need to go to surgery, and they will put a metallic implant. It will typically be titanium, and then you will live with that implant for the rest of your life. And it's not a big deal. You just, you know, when you go through the airport scan, they will make a noise, but otherwise it's okay. It is a bit more deal for young kids, because kids that are still growing, they need to do a second surgery to remove the implant. So that's a bit of a problem. So ideally what, you know, medical doctors were hoping to is to use magnesium. Magnesium is a biodegradable material. So it would be great if you could use magnesium, because by being biodegradable, this means that you're hoping for a situation like this, where maybe you have your tissue or your bone that has broken and needs to heal. You put your implant, and then as your bone is recovering stiffness, your implant is degrading. And this will be the ideal situation. The problem that we find is that magnesium degrades too fast. So this is, let me write down here, this is the ideal situation. So what I'm plotting there is, you know, the stiffness of your, some sort of measure of stiffness of your tissue or your versus time, or your tissue or your bone, and then you want your broken bone to grow until it's completely healthy, and then you want your magnesium implant to degrade progressively until, you know, it disappears completely once your bone is healthy. This is what you're hoping for. The problem is that magnesium degrades too fast. So you get something more like this. So there's not enough time for the bone or the tissue to heal. That is basically the problem. And this is a problem, and a lot of people are doing research on this, and they're trying to come up with solutions. Some of the solutions, as you can imagine, is, you know, playing with the geometry maybe. That I'm not sure if it will get much far. People are also discussing, for example, alloying. You need to be careful, because you need to add basically components that are still biodegradable, that are biocompatible. But if you can think of good alloying techniques, or if you could think of a composition that will still remain biocompatible and biodegradable and will slow down corrosion, that will still be useful. Or one alternative that seems a bit more promising is composites. Maybe you can make a composite of magnesium and another material that is also biocompatible, biodegradable, but has a different biodegradation rates. So what we thought is, okay, everyone working on this topic is doing so experimentally, so we thought maybe there's an opportunity for us to develop a phase field corrosion model, biocorrosion model, that basically allows us to quickly test those conditions. And this is worked together with a group of Javier Llorca at India Materials in Madrid, where they run the experiments. And basically the idea is the same as before. So this is the boundary problem that you have. So similar, you have a metal undergoing mechanical stresses. You may have a corrosion product. The electrochemistry changes a little bit. It's a biological fluid, but otherwise it more or less remains the same. You use the phase field to describe the evolution of the corrosion front, so it's very similar formulation. And then, well, there's multiple things that you can compare against experiments. You can compare, here you can see the average pit depth. Here you can compare the hydrogen gas, so there's some release of hydrogen gas with these reactions. So there's multiple type of tests. They do coin tests, they do this kind of bar test. We basically compare the model with all of those experimental measurements, and we seem to be in relatively good agreement. So I think we're quite happy with experiments. And this is useful. I think I have more experimental data point here. So this is a paper that we just got accepted in a few weeks ago in Acta Biomaterialia. The agreement with experiments again seems to be very good. And I think the key point that I want to emphasize at this point is that if the good thing of being able to agree with experiments is that not only you can do in vitro tests with a computational model, but you can also do in vivo predictions. So we're not allowed to do experiments on humans. Doing experiments in animals is also something that is rare and maybe only allowed in some countries and to a minimum. So a model is very convenient because it allows us to compare the model against experiments, so what we call in vitro conditions, and then take the model and change a little bit of electrochemistry just to resemble more what happens inside of the human body and capture what we know as in vivo conditions. So this is again another strong argument in favor of these models. Not only we can test ideas quickly, we can test those ideas under conditions relevant to body fluid and the conditions that resemble in vivo scenarios. So yeah, this is an area that I feel quite excited about what we're doing in this front. And again, you can model anything you want. So for example, you can model a stent, and you can see the degradation of the stent as a function of the corrosion current density and so on. So I think this is you can not only model small scale, but you can also model, not only you can model the experiments that you do in the lab, you can also model the large scale phenomena. And for example, this is a case with the screws. People want to use magnesium plates and screws for this kind of implants, and these screws seem to degrade too fast. And you can see here that we can simulate precisely the degradation of those screws, and we can then change things in the screw, the alloying, we can change the shape, we can embed the screw into some sort of composite. We can do all of those things and predict the degradation of the screw in time. That's the idea. Okay, now I'm going to the topic that several of you have raised before, and this is a key aspect when it comes to predicting natural conditions. And so this was worked together with Carmen Andrade, which is now linked at CIMNE. Carmen Andrade is a very senior and distinguished scientist in the area of concrete corrosion, and they're very interested in concrete corrosion and understanding a number of phenomena. One is, for example, what happens they're always interested in the natural corrosion conditions. So they always do their experiments with an impressed corrosion current density, so they always apply a current, but they know that in nature there's no current being applied, so it's natural charge conservation conditions. So they wanted a model that was able to simulate those charge conservation conditions. And not only that, they were also interested in a few items. They're interested in what happens with corrosion when you're lacking oxygen. So apparently, sometimes they build corrosive structures in the sea. For example, there's some oil and gas platforms in Norway that are built this way, and they see some corrosion there. Of course, the corrosion here refers to the reinforcement of the metal, of the concrete. So they have metal reinforcements, and that's what worries them, the corrosion of metal reinforcements. So they were interested in that, so they were understanding on how much oxygen you need to continue a corrosive reaction. We know that oxygen favors corrosive reactions, but can you survive? Oh, my internet connection is not very good. I don't know what's happening. I hope it's being recorded well. So can you survive without oxygen? Maybe you need a little bit of oxygen to trigger the reaction, but can you survive without the oxygen? There were questions about, if you have a lot of electrolyte or versus you have a very thin layer of electrolyte, a small exposure to maybe water. And all of those conditions are again, and also this interest on knowing where you have the cathodic and anodic reactions. And all of those conditions are under charge conservation conditions. So they want to understand natural corrosion reactions. And in the experiments, you always, you accelerate corrosion, so you apply a metal potential or a corrosion current density. In COMSOL, which is I think the only kind of commercial finite element package, or one of the few who can simulate corrosion, this is the way to go as well. But if you have your own finite element code, and this code is available for everyone to download, this is a MATLAB code, then if you have your own finite element code, then you can enforce charge conservation, and then you don't have to apply a current or a potential. You just let things happen due to natural free corrosion. And this is what we did basically, and once you do that, then you're able to understand a bit more, you can build these maps of what is the corrosion current density depending on, the size of your peat, the availability of oxygen, what's happening with cathodic and anodic reactions. But more importantly, in these models, you are not forced to define where cathodic and anodic reactions happen. So you can say, my anodic reaction, your model can tell you. You can assume that it's going to happen all over the domain, all over your boundary value problem, your anodic and your cathodic reaction. And then your model will tell you in which areas of the domain the anodic or the cathodic reactions are actually happening. So this is what you see here. So this is another of the questions that the people in the concrete community seem to have. So, okay, we have this metal here. Under which conditions, if I have pits, how do those pits need to be close to each other? Under what area do I need, a layer of oxygen, a layer of water? And you can see those things here. You can see here where the cathodic reaction is happening, how the pH is changing within your solution for a given, metallic bar, reinforcement bar, and what is the cathodic and the anodic reactions, where are these spanning? And we can, we learn a lot of things there. One of the papers already published, the other one will be published soon, so I'll let you know if anyone is particularly interested. I'll point you. I'm happy to send a copy if you're interested in. But this is the idea. You are not limited to model and applied current or applied potential. You can just see things as they happen in nature with this kind of enforcing charge conservation. In continuing with the concrete, we have been quite interested in looking into corrosion-induced cracking in reinforced concrete. This is work done by Eugen Korek, a PhD student of mine, who's a postdoc in the group, and who finished his PhD recently. In fact, he was quite productive. His thesis just was awarded to the prize, the Roy and Orr Award, which is the Roy Owen Award is the prize that recognizes the best thesis in computational mechanics in the UK. So what he basically combined is our understanding of corrosion and electrochemistry with face field fracture as well, because this is one of the issues that we see in reinforced concrete. You have corrosion and then you have some rust, and due to the different density of the rust and the metal and the matrix, you get cracks. So he was able to predict the evolution of cracks. And the key point that he wanted to do is that by coming up with a different hypothesis on the evolution of corrosion, he wanted to incorporate the underlying physics and kinematics of this process, says that we could calibrate our predictions with accelerated corrosion experiments and then run virtual experiments under natural corrosion conditions. So this is what you see here. And then we were able to understand finally why, impressed current tests, accelerated current tests, underestimate the degree of corrosion. And then another aspect, so this is a work from Machi Maku, who is a PhD student in my group. So he's a physicist, so he likes very much these kind of things. He's interested in accounting for the role of the electric double layer. I think the jury is out whether phenomena like the electric double layer, which are things that happen within a very small boundary layer near your metal, so it will be atomistic things, would matter or not. He implemented, and we saw that you could capture some experimental data that otherwise you capture in a bit more crude way. As an engineer, I don't know if this will be a first order effect, I must confess, but I think it was quite interesting work, and basically you bring an equivalent circuit and you can capture this sort of atomistic phenomena at the continuum level. But then finally, the aspect that I want to discuss a bit more time is coming up with a generalized model for stress corrosion cracking. So I've been discussing hydrogen embrittlement completely independent from corrosion, and this is mostly due to the fact that the interest in hydrogen has shifted. Before hydrogen, people interested in hydrogen embrittlement were mostly people coming from corrosive environments. So applications dealing with corrosive environments such as H2S or oil and gas applications, for example, very aggressive corrosive environments. Now we have moved to situations where we care about hydrogen gas for energy and transport, green hydrogen, and therefore we don't really care that much about corrosion reactions. I mean, there's still a lot of people that care about corrosion, hydrogen coming from corrosive reactions, but there has been a shift in the community. But back in the day, hydrogen embrittlement was considered to be a category within stress corrosion cracking. Now we no longer typically use that terminology because we have hydrogen embrittlement coming from hydrogen gas and other conditions where there's nothing to do with corrosion. But very often hydrogen embrittlement will be a category as part of stress corrosion cracking. And a big deal for the people working in this community is that basically you have two types of mechanisms or stress corrosion cracking mechanisms. One would be anodic dissolution. So your crack is growing because you are removing material ahead of your crack. So this is what you see here. You are removing material here. So your crack is growing due to anodic dissolution mechanism. So some sort of localized corrosion mechanism and a combination of that with mechanical rupture. And sometimes your crack is growing due to that plus the uptake of hydrogen. So it's a very complex problem where you don't know. Sometimes under certain regimes hydrogen dominates and the crack is growing mostly due to hydrogen with maybe some help from the corrosion process that you see, for example, in cathodic protection conditions. And there's some other conditions you may have, for example, in the anodic regime, you have a little bit of an uptake of hydrogen plus the dissolution of material. So in some areas they are more synergistically combined, and in other material environments, it's anodic dissolution what drives all together. So this has been always a nightmare, a bit of a headache for the people working in this community because they don't really know when you get cracks that are growing due to hydrogen, when they grow due to anodic dissolution, when they grow due to the combination of both. So the idea here is that in principle we could combine everything that I told you this week into one generalized framework and then let the model decide. The model is going to simulate anodic dissolution, the model is going to simulate hydrogen embrittlement, so the model will decide how much of each contribution is driving fracture. So here we're becoming a bit greedy, we're just solving everything. This was a GMPS paper that we published a few years ago. My postdoc Chuanji Kui was leading the author, was the leading author. And here we're becoming a bit greedy and you have a bit of everything here. So I think it's a good idea to finish with this part of corrosion because it kind of combines everything that I've been telling you this week. So we have a displacement problem, that is the balance of linear momentum, plus you see that we have two phase fields, a phase field for dissolution and a phase field for the fracture. And here they're combined. This H is the degradation function. In this case, the degradation functions multiply each other. Whether this is the best way of combining them or there's a better way, I don't know. This was the first time this was done, where you had a phase field fracture and a phase field corrosion. It seemed to work out okay in that you don't see, because both degrade the stiffness, you don't see phase field corrosion and phase field fracturing happening independent from each other. They seem to progress in a combined way. Then you have the phase field fracture problem, where you have the evolution of the strain and density, which is degraded by both phase field components, and you have a fracture energy that is dependent on the hydrogen concentration. And by the way, here I changed a little bit the notation. So different to all the previous examples that I showed you before, the phase field is going to be equal to 0 in the damaged area, so the electrolyte, and equal to 1 in the metal. So this is different. I just changed the notation. So before, when I talk about phase field before, now it's going to be 1 minus phase field. There's some people in the community do it this way. I did it this way because in corrosion we normally use phase field equal to 0 in the electrolyte and phase field equal to 1 in the metal. So I wanted to retain equal to 1 in the undamaged metal. Then you have the hydrogen transport equation with some uptake of hydrogen. Then you have some ionic transport equation. Then you have the corrosion equation, phase field corrosion for the phase field dissolution problem. And then you have all the electrochemistry as well. So everything in there, it's just all embedded. And this is very powerful because it allows you to simulate stress corrosion cracking for any environment. So you don't have to make any a priori assumption saying, okay, in this case, cracking is going to be driven by hydrogen embrittlement or anodic dissolution or maybe a combination of both. Here, you can handle any arbitrary environment. So for any choice of environment, you can capture what is, for example, your threshold toughness. And this is what you see here. This is compared against experiments for a very wide range of environments. And you can see that we can capture the low values that you get in the anodic regime where there's a bit more hydrogen dominated to the free corrosion condition, and again the anodic dissolution condition where you have a combination of both hydrogen uptake and also some anodic dissolution processes. And you can do that while at the same time as you can capture the evolution of the electrolyte and the corrosion front. And by the way, there's some aspects that I'm not discussing here that I would like to refer you to this paper with my postdoc Tim Hageman in CMME 2 years ago now. there's a lot of things that are important here. For example, one of the things that is important that I'm not discussing for the sake of time is if you're dealing with a fluid flow, if you need to capture how the electrolyte behaves inside of your crack, you have a fluid flow there, you need to know your crack opening. How do you do your crack opening when you're dealing with crack with a phase-field description of fracture? We have a smear representation of your interface. This is a problem not only for corrosion, it's a problem also for example, the hydraulic fracture community, right? They're interested in fluid flow, so they need to know the crack opening. There's multiple ways. The hydraulic fracture community has developed many ways. Some going from very simple, you get a strain field ahead of the crack in your crack size, and from the strain you develop displacements, and there you interpret the thickness. There's various approaches that different people have done. We propose in that CMME paper what I think is a more rigorous treatment. It's still quite complicated, so I don't think the last word has been said on this, but we developed what I believe is a rigorous treatment in this CMME paper, and also treatment of reactions and electrochemistry and so on. So you can take a look at that one there. I'm missing one slide here. I don't know what I did with that slide. Maybe I'll remove it thinking that I wouldn't have time. But what was interesting is that, it's a pity I don't have that slide, but I'll tell you in words. So another thing that we used this generalized model was to understand some classic experiments that Gruhl, a German scientist, did in the 80s. And it was quite good because he did some experiments. He was trying to understand whether aluminum alloys in the presence of corrosive environments will fail due to another dissolution or hydrogen embitterment. And he did some very clever experiments where he basically did some tests on some, basically he was dealing with some cylindrical samples. And these cylindrical samples, I think they had this shape, yeah. So they were cylindrical samples, so you can imagine a cylindrical sample like this. And then they had a notch on the other side. Yeah, so let me just do a drawing. I'm not very good at drawings, but hopefully you're understanding what I'm doing here. Well, it doesn't matter, yes. Imagine a cylindrical sample with a notch on the sides. So then what he did was he put a corrosive medium in the inside of the cylindrical sample. So this was a very corrosive medium. And then in the outside, he protected this surface. So not only was exposed to air, but also protected. And here you have a very aggressive corrosive medium. So then he said, if failure happens here, in the inside, this means that it's anodic dissolution what is driving the process. But if failure happens near the notch, before, he also did some tests in air. In air, you'll get failure in the notch, but you'll get at a very high load. If failure happens near the notch, that will mean that it's hydrogen driven. Because remember, what you see here, basically, if I zoom in here, is that you'll have some corrosive reactions happening here. That will generate hydrogen atoms. And remember, those hydrogen atoms like to go to areas of high hydrostatic stress. So if my cracks are here, this means that my hydrogen actually travel there. So then he did a set of experiments and basically hold the load constant and see how long it took to fracture and where fracture occurred, whether it started in the inside or the outside. And it was a very set of clever experiments, and actually fracture occurred here. So he concluded that hydrogen was dominant in environmentally assisted cracking of aluminum alloys, and this was a landmark paper for the field, and the community switched their attention to hydrogen because of this. What was interesting that he predicted failure to occur after, I'm speaking by memory, but I think it was like 11.2 hours. In our model, where we tried to do things without any fitting, we predict failure to occur after 10.9 hours. So it was a small difference, but we tried not to fit. We could have fitted model to get the same answer. We tried not to fit, and we got something that we tried to put all the numbers before running the simulation, so we got quite close. But we could also take the model and change the environment that Gruhl did his experiments on. He was interested in a particular environment relevant to aluminum alloys, and this is a big problem for aerospace. But we changed the environment and see under which conditions actually anodic dissolution will play a role. And we could see that under more aggressive conditions, anodic dissolution will dominate over hydrogen. So I thought that was quite interesting, and it's a pity I forgot to include that slide here, because I thought that was quite interesting. I mean, it's just an example of what you can do with kind of a generalized stress corrosion cracking model, where again, the idea is that, going back to the beginning, you try to remove assumptions. You let the model, by solving brute force all the physics that are happening, let the model make decisions by yourself. So just to conclude, I think that it's quite exciting that you can combine phase field and multi-physics modeling to resolve the physics of localized corrosion. We can finally, the combination of these two paradigms, the ability to solve coupled electrochemo-mechanical phenomena as they happen in reality, and the ability to solve how that interface is evolving in time and how this is coupled with all of those electrochemical phenomena allows you to resolve things at the mesoscale without any assumptions, eliminating fitting parameters, eliminating assumptions, just doing brute force calculations. Again, similar to the phase field models for hydrogen, the framework is very flexible. This is continuum mechanics, finite elements. We have incorporated a few things: activation and diffusion control corrosion, pit interactions in 2D, 3D, intergranular corrosion, secondary particles. So in principle, the computational tools are there, and you can capture each of those elements. And then what we did was to extend it in multiple directions to incorporate physics of corrosion. So corrosion is a complicated model, but it's a very complicated problem. But we can incorporate those complicated phenomena. There's many things that one can incorporate. The ones that we try to incorporate, well, first is the role of mechanical fields in both enhancing corrosion rates and disrupting the passive film. There's a sensitivity to microstructure, to crystallographic texture, the influence of the local electrochemistry. We have quite a lot of fun in biocorrosion, this area where we're trying to understand the in vivo corrosion of biodegradable materials. We're also interested in reinforced concrete structures under both accelerated and natural corrosion. We incorporated also the role of the electric double layer, and then finally the interplay with hydrogen embitterment mechanisms. Okay, that's all. Yeah, it's a bit more than half past, but this is perfect to do a coffee break, I think. So maybe we can be back at, 11:05. I think that's a good time. Perfect. Group photo, of course. Don't forget about that.